So our next speaker is Chana Weil-Kennedy. She's a PhD student in Munich, and she will talk about branching immediate observation Petri nets. And carry on.
Okay, thank you for the intro. And yeah, so I'm going to present branching immediate observation in Petri nets, which was a joint work with Javier Esparza and Michael Raskin at the Technical University in Munich. And so I promised to show that it's a strong class with simple reachability, but to be a little more honest and a little more clear, and it's actually, I'm going to show that it's a non-semilinear class with PSPACE reachability. All right, so thanks to our previous speaker, we did get a freshening up on what Petri nets are, but I'm going to give you an example to, so that everyone remembers Petri nets and how they work. And this one is, of course, going to be an example of a branching immediate observation Petri net. So can you guys see my cursor? Okay, so here's an example of a Petri net with places S like server, C like client, W like worker, R like response, and transitions 1, 2, 3, 4. Which models a client-server interaction, where, for example, the client wants to know the current number of votes in an election process. So if there's a server and a client waiting, then T1, transition T1 is enabled and can fire, and morally the server creates a worker. Then the worker, via transition T2, can create a response. A client, one of the 3 waiting clients can observe the response and leave. Another client can observe the response and leave. And then a response may expire via transition T4. And then if the server is still available, if there's still a client waiting, there can be a new worker created, a new response, which the client observes, and then the response terminates. So in Petri nets, when we talk about a configuration of a Petri net, it's where the tokens are located in each of the places. So for example, we started off with the configuration, which we call a marking in Petri nets term. We started off with the marking in which there's 1 token in S, 3 tokens in C, and 0 tokens elsewhere. And we just saw a firing sequence via which we can go from this marking, this first marking, to the marking which puts 1 token in S and 0 tokens elsewhere. So given a Petri net and given 2 markings, the reachability problem is, can the first marking reach the second marking in this Petri net? And so this reachability problem is very central to the study of Petri nets and equivalent things like vector addition systems with states. So it's important, the reachability problem is central not only when we're verifying things over systems modeled by Petri nets, usually concurrent systems, but it's also important because there are many problems in other domains of theoretical computer science that are interreducible with the reachability problem in Petri nets. So here I just put examples from formal languages and logic and process calculi, but if you're interested in the interreducible problems, there's a good survey by Sylvain Schmitz, which lists these. Now the problem, as Slavik said, is that in the general case, the reachability problem is very, very hard. It has non-elementary complexity, as was shown by members of the audience last year. And so it's natural to want to study subclasses of Petri nets that have a more manageable reachability problem. So the model that I am going to show you, branching immediate observation nets or bionets, is a generalization of 2 such subclasses. The first of which is branching parallel processes, BPP nets, also called communication-free nets, which have been extensively studied from the 90s until recently. And they're a class of Petri nets, which is entirely defined by their transitions. So their transitions have to be of the form which is here. So there's one input place, and when the transition fires, there can be multiple output places. Now, there can be weights on the arcs. For example, here, this would put 2 tokens here and 1 token here and 1 token here. There can not be 0 input places. There cannot be more than 1 input place, but you can have no output places if you wish. So in Petri nets of this subclass, there is token creation and destruction. And we say they're communication free because if we think of the token in the input place of the transition as a process, it can branch into multiple processes or disappear without having to depend on where any other of the processes in the system are. So that is why we say it's communication free. The other Petri net subclass that bionets generalize is less studied. It was studied by Javier and Michael and I last year, and they're called immediate observation nets. We had studied them because they had a good application domain to population protocols, which we were studying. But basically, they are also defined by their transition relation. So transitions are of the form I indicate here, where there's one purely input token, which observes that there's a token in another place, and then can move to a new place. So these Petri nets do not create or destroy tokens, so we say they're conservative, but there is a minimal form of communication or dependency on where other tokens of the net are. All right, so our bionets are really a generalization of both of these. We have transitions of this form, which have one purely input place, possibly multiple output places, and multiple observation places. So here, if we fire this transition, we get this distribution of tokens. It's possible to have weights on the output arcs. It's possible to have no output places at all, as in BPP nets. It is still not possible to have multiple pure input places, but this time it is possible to have no input place at all. So this seems like a kind of messy definition with lots of possibilities, but, oh yeah, sorry. And I forgot to say, you can have any number of observation places as well. So all of these cases are subsumed in this equation, where this dot T is called the presets of transition T, and this is the post set of transition T, and they're multi-sets. So the preset of transition T is the number of input places, and the post set of transition T is the number of output places and it's a multi-set because we can have weights on the output. And so a branching immediate observation net is a Petri net in which transitions all verify this. There is at most one pure input place. So there's token creation and destruction, and there's a sort of communication. And of course, the example I showed you previously is a branching immediate observation net. I'm just going to call them bionets. So it's a bionet, for example, because all of its transitions are biotransitions. For example, transition T3, there's a token in C which observes that there's a response and leaves. Okay, so that's the definition of bionets. Now, where do they fit in the complexity of their reachability problem? Where do they fit into the literature? So they subsume BPP nets, they subsume IO nets, and BPP nets have an NP-complete reachability problem. IO nets, we proved last year that they have a PSPACE complete reachability problem, and then we've got this non-elementary overhead. So we show that bionets have a PSPACE complete problem still. And so this makes them pretty manageable. And so they're interesting because until now, as far as we know, every PetriNet class that is unbounded, where there can be token creation, which has a reachability relation that is provably simpler than the, sorry, not a reachability relation, a reachability problem complexity, which is provably simpler than the general case. These nets always have semi-linear reachability sets, okay? And this is not the case for bionets. So the proof for that is actually pretty easy. If you know, there's this classic example in the Hopcroft-Infantio of 79. It's an example of a three-dimensional vase, which has a non-semilinear reachability set. And if we directly translate it into a Petri net, we get this Petri net, which is in fact already simply a bionet. And for those of you who don't know the example, I can show you, I can give you an intuition of why this net doesn't have a semi-linear reachability set. So we've got, so C1, C2, C3 are morally the counters of this three-dimensional vase. And then P and Q are morally the states of this vase. And the token can circle in a cycle from P to Q, and C1 keeps track of the number of cycles. And when there is a token in P, then the token in C3 can, all tokens in C3 can move to C2. Then when P is in Q, all tokens in C2 can move to C3, doubling their number. And then we go through the cycle again. All the tokens of C3 can go to C2. And then when we cycle again, they double again, and so on and so forth. And so we get that the number of tokens in C2 plus C3 is smaller. Weekly computes is smaller than the exponential of C1. So this bionet can generate exponentiation. And so it's more or less easy to see that it has a non-semilinear reachability set. Okay, so the interesting part, and what I'm going to spend the rest of my talk on, is that I would like to convey to you how we get a PSPACE upper bound on the reachability problem of this class. Because I think that, although I won't go into details of the technique, I think it should be reapplicable elsewhere, and it's interesting. All right, so the PSPACE hardness of the reachability problem for bionets is via reduction from the acceptance problem in linearly bounded Turing machines. And I won't go into details. And the PSPACE overhead is via main theorem, which when we're given a firing sequence between two markings that proves reachability, we can modify this firing sequence to obtain a new firing sequence, which is smaller, it has less tokens, and it's shorter for a certain definition of length. So I'm going to try and walk you through this main theorem. So given a bionet, which has n places, and given a bound gamma on the number of tokens that each transition can produce, if a marking M0 can reach another marking M, then there exists markings M1, M2, ML, transitions T1, T2, TL, and constants K1, K2, KL, such that there's a firing sequence from M0 to M, which goes through these intermediate markings. And between each intermediate marking, there's a transition Ti iterated Ki times, okay? And we show that we can find such a set of markings, transitions, and constants such that the number of such intermediate markings is bounded by an exponential which depends on the number of tokens in the final marking and the number of places in the net, n. And when I say the number of tokens in the final marking, it's in unary, like really just the number of tokens. So we have a bound on what we call the accelerated length. Note that this is not exactly the length, because the length of this firing sequence is K1 plus K2 plus KL. And yeah, but so we have a bound on L. And we have a bound on the number of tokens for each of these intermediate markings. And this bound is exponential in all the inputs of the problem. So in the number of places n, in the maximum number of produced tokens gamma, in the number of tokens of the initial and final marking. Okay, so if that seemed a little complicated, it's really just a simple idea, which is that if we have a firing sequence in this net, which can create and destroy tokens, and it goes from M0 to M, well, the token creation can go basically as high as we want, and then the token destruction. And so we can have really a lot of tokens in the intermediate markings in an arbitrary firing sequence, and it can be very long. And what we show is that we can find one which has less tokens and is less long. All right, here I just repeated the main theorem in a smaller form. So why does the main theorem give us a PSPACE algorithm? So by Savich's theorem, we know that it's enough to give a non-deterministic PSPACE algorithm. So we want an algorithm that decides if marking M0 can reach marking M. The algorithm is very easy. We guess the first of these intermediate markings, M1. Then we check that there exists a transition of the net and a constant K such that M0 can go to M1 via T iterated K times. Then we guess the next marking M2. Then we check that we can go from M1 to M2, and so on and so forth. Why is it in PSPACE? It's in PSPACE because we only need to remember M0, M, and M1, or M1, M2, and M, or M2, M3, and M at the same time. And by the main theorem, we know that each of these intermediate markings has at most an exponential number of tokens in the input variables, and therefore we can write in a log of that, so in PSPACE. So we can keep these markings in mind in PSPACE. And this operation, checking that there is a transition of the net and some iteration count such that M0 can reach M1, is also in PSPACE because of, well, there are various reasons, various ways of showing this, but one of them is we know a token bound on M0 and on M1, and then we just need to check that there's a way of going from one to the other by iterating a single transition. Okay, I hope I've convinced you that this gives us an NP-space algorithm relatively easily. Okay, so but how do we get this main theorem? How do we bound our firing sequence? So one of the main ideas is to de-anonymize tokens. Look at token histories. Normally tokens in a net, it doesn't matter if there are two tokens in queue, it doesn't matter which one performs what transition. They're in a certain sense anonymous. And here our idea is just to look at token trajectories inside of a firing sequence. So just to make this clear, I'm going to show you on an example of a small net, which has 3 places P, Q, R, and 2 tokens in Q and 1 token in P initially, which are shown here. And then let's say there's a transition which observes a token in Q and then takes a token from P and puts 3 tokens in R. So this would be written in this way. We would go from M0 to M1. In M1, we would now have 3 tokens in R, and we would still have the token in Q and still have the token in Q that haven't moved. Then if we had a transition which observed a token in R and took a transition from Q and put 2 back in, we would have this distribution of tokens. And okay, then if we had a transition which destroyed a token in R by observing a token in Q, we could have this. And then with another transition that I won't describe, we could have this. All right, so here we have what I'm calling a history of token trajectories, which are trees because there can be token creation and destruction. And now that we have these token histories, we want to divide the nodes of these trees into 3 types. The first type is the final tokens. They're the ones who appear in the final marking of our firing sequence. Okay, so here in the final marking, there are 2 tokens in R, no tokens elsewhere. And we color in blue all the tokens which in the future will be final tokens, which will produce final tokens. So here, this token in P produces what will be the 2 tokens in R. That's deterministically defined and relatively straightforward. The second type of token we identify is, so they're in fact not tokens, but token moments, tokens at a moment in the history. So these are the helper tokens. Now the helper tokens are morally the tokens which allow the rest of the history to happen. For example, in this transition here, the token in P needs to observe that there's a token in Q to take the transition which puts 3 tokens in R. And so the fact that there's a token which is in Q and M0 and stays in Q until M1 allows this, it helps this transition to happen. For the second transition, it was an observation of token in R, which allowed a token in Q to split into 2. And we can identify helper tokens over and over like this, knowing that the helper tokens can also be final tokens. Now, the blue tokens, the final tokens, were deterministically chosen. We don't have a choice. But for the green tokens, the helper tokens, it could have been a different set. We could have been observing not this token in Q, but this token in Q to allow this transition. In any case, what we do is we take if M0 can reach M, then there exists a firing sequence in which we can identify final blue tokens, helper green tokens, and the rest. And we rework this firing sequence in 3 steps. First, we definitely keep the token trajectories that have final tokens in them, including if they create other tokens that are not final, because we can't simply take away this branch in a transition that creates 3 tokens. So we keep these. And then second, we reduce the number of helper tokens. So here, for example, I have 3 moments in which there's a token in Q, in place Q, which acts as a helper token. And this helper function is done by 3 different tokens. And what we want to do is have it be done by only 1 token. So what we do is we identify the prefix tree, which leads to the first moment where Q is a helper. We identify the last suffix tree from which Q is a helper. And then we copy and paste these 2 together and keep Q, keep a token in Q in the whole time in between. And so now there's only 1 token, which is the helper in Q at this moment in the history, at this moment in the history, and at this moment in the history. This token is just staying there until it leaves. All right, so in this way, we can reduce the number of helper tokens by modifying the firing sequence. Finally, we cut out repetitions of the multi-sets of final tokens and helper tokens. So we show that we can ignore all the other tokens, which are neither final nor helper, identify when there are repetitions of final plus helper, and cut out these repetitions, thus obtaining a shorter firing sequence. And we do this over and over until there are no repetitions of the final plus helper multisets. All right, so there are at most m final tokens per intermediate marking of this firing sequence, where m is, well, the number of n tokens. There, we show that we can make it so that each intermediate marking has at most n square helper tokens. And using this and the fact that we've cut out all repetitions of these two, we have a bound on the accelerated length, or on the length of this history. And then from this bound on the accelerated length, we can get a bound on the number of tokens in the intermediate markings. All right, so I have a bit more time. So I'll show you another consequence of the main theorem, which, so now we've basically shown, or I've given you an idea of the proof that there is a p-space reachability algorithm for bionets. But this is a theoretical algorithm. And so it's better if we have efficient procedures in practice for verifying reachability and other things on bionets. So there's a notion which Saramia did evoke in his talk of flatness. So we consider flatness as introduced by Leroux and Sutre in 2005, where we say that a Petri net is flat if there exists a sequence, T1 star, T2 star, of transitions of the net, so kind of like a regular language over transition words, such that a marking M0 reaches a marking M if and only if it can reach it via a firing sequence, which is a word of this regular language. So if there exists a K1, K2, KL, such that M0 can reach M by T1, K1, T2, K2, TL, KL. I hope this is not too small on your screen. Now, okay, this is actually a kind of simplified version of flatness, but it happens to go with what I want to say. So BPP nets, these branching parallel processes, and IO nets, the immediate observation nets, are both flat. But Leroux and Sutre also show that a Petri net is flat if and only if its reachability set is semilinear. And we know that bionets do not have a semilinear reachability set. So we know that they cannot be flat. But we show instead that they are pre-star flat. So this is a slightly weaker property where the sequence T1, T2, TL star depends on the final marking. So for all M, there exists a sequence T1 star, T2 star, TL star, such that a marking M0 reaches M if and only if it can reach it via a word of this regular language of transitions. And in the main theorem, we show that M0 can reach M if and only if, well, no, sorry. If M0 can reach M, then there is this firing sequence which has accelerated length, which depends only on the places of the net and on the number of tokens in the final marking M. So this gives us directly that bionets are pre-star flat. And why is it interesting to have this pre-star flatness? Well, it's interesting because there are existing analysis tools for systems that are flat, but also what is called post-star flat, but which could be made into pre-star flat. For example, FAST or LASH or CHEX. And so because of this, we can use these tools on bionets. All right, so in conclusion, I have presented to you branching immediate observation nets, which have a p-space complexity, p-space complete complexity for the reachability problem, and which are non-semilinear. And things that I didn't put in this talk, but that are also true, is that this reachability result, p-space completeness, holds not only from a single marking to a single marking, but also from a set of marking to a set of marking for a certain type of simple set, which can be possibly infinite, and which we call cubes, and which I can tell you about if you want. And also that this p-space completeness holds not only for reachability, but also for coverability, liveness, and more. And in the future, and this is where you guys can maybe help, we would like to try and investigate the consequences of this reachability result in link, for example, to things that bionets can model, like chemical reaction networks or other, yeah, things like that, but also in relation to other fields of computer science, like process calculi and formal languages. And that's all.
Thanks, Chana, for the very nice talk. Instead of clapping, there will be just an awkward silence.
Thank you.
So there were two questions. One was about p-space hardness, but Mihail already answered it, whether you can just use p-space hardness of the previous result. And Vincent had a question, but he answered it himself, whether some constant L was bounded.
Okay.
I have a question myself.
Sure.
It's about this class. It's essentially some restriction on the general Petri nets. How kind of, I mean, it's very important in this that you have only one input token, because this allows you for this tree structure. And I guess if you allow for two input tokens, then you're already as hard as in general Petri nets. But is there some, is it in a way like the most general class for which, like, do you have some open problem of like an extension of this class? Is there some natural way to look at something?
Well, okay, so like you said, this entirely depends on the fact that we have at most one input place. And then, I mean, you can have any number of destination and any number of observation, but observation is just a way of looking at it, which we inherited from this immediate observation class. So I mean, I feel like it's really this minimal condition to keep p-space, or at least that's how we see it. We might be wrong and there might be something we're missing, but we feel like this constraint on the cardinality, that the preset minus the post-set multi-set difference is at most one, that is the minimal thing for p-space completeness via this technique. Okay. So I don't know what type of generalization.
Yeah. I had none in mind.
Yeah. No, I mean, it's a good question. But yeah, so what we use in our proofs, what we use in our construction is the fact that there's at most one input place, and since that's exactly the definition, I'm not sure. Yeah.
Okay. I guess there are two more questions. Hoffman has a question, and Wojtek. You can ask your questions in any order. Okay.
Yeah. Hoffman? I finally managed to open the chat as well as share my screen, so I can actually see them now. Wojtek, do you want to? Okay. Okay, so Piotr, your question was, I want to ask about intersection of the reachability sets.
Yeah.
What do you want to ask?
So basically, have you tried to investigate what is the complexity of checking if, well, you suppose that you have two nets, but well, on the same set of places, but with different transitions, of course. And you want to ask if the reachability sets from some two different configurations are well, have non-empty intersection.
Okay.
Or basically you define some interface, like there are some places that that you consider final, and you run your PetriNet, and you want to build some configuration with tokens only in this final configurations.
So I think that we can have a p-space complete thing for that too, because so when I was saying that in the other results of this conclusion site, so I say that it's also possible for sort of sets of markings, and I say that this also holds for coverability, liveness, and more. And in the more, there's that we can do intersection and union and negation of this kind of question. So we could have, I think, intersection of the reachability sets. I think it would still be PSPACE complete.
Okay, so then I would like to make some comment, I think, because there is a fun, well, an interesting way of generalizing this, I think. So, well, if you take your class and revert all arrows, then you will get very, well, kind of a dual class in which instead of branching, you are kind of gluing together.
Okay, I didn't evoke this. They're called MIO, merging immediate observation nets. And yeah, of course you can reverse it.
And then if you will do the following thing. So first you will put such a branching net, observable this bionet, and then you will glue it using some kind of interface, some places, with some net which will be this MIO-net. So first you will have like branching part of your system, and then you will have like gluing part of your system. Then checking if you can go from the initial configuration to the final configuration should be equivalent to checking a non-emptiness of intersection of two bionets. So this MIO-net kind of reversed.
Well, okay, maybe.
Yes. And then
it would be worth looking at, but one of them goes through pre-star and one of them goes through post-star, so it wouldn't be direct, at the very least.
So, so this I didn't understand. What's the difference here?
You want me to tell you, or are you telling me something?
Yeah. So well, because from what I understand, what you say, then you can, using these techniques that you have, you can generalize to kind of bounded number of phases nets, and each phase is like first unfolding, then folding, unfolding and folding, like or branching and gluing, and you can have some bounded number of such phases in your system, and it still will work like this.
Okay, that's interesting. Maybe, are you going to be in the break afterwards?
Yeah, I think I can be.
Then maybe we can talk about it then.
Okay.
Yeah.
So I think
Wojtek, you had a question too?
Yeah, so I really like the class. And when you talked about the BPP, I recalled that some years ago I was working on bisimilarity on BPP, and there are like known results on bisimilarity, but it's essentially bisimilarity checking is PSPACE complete. And for general Petri nets, it's undecidable. So I wonder, do you know anything about bisimilarity checking on
so sadly, I do not. So when I mean, I am aware that there is work on bisimilarity and it's PSPACE for BPP nets, but I really haven't worked on that at all. I basically realized it when I was looking for references, and so no. But I would be very interested, because I know that's like the interesting question for BPP nets, and I'd be very interested in seeing how it kind of relates to bionets. So no, I haven't, but I would like to.
I just think it's a good candidate that maybe bisimilarity checking is decidable there.
Yeah, so bisimilarity checking on bionets. Yeah.
Okay, thanks.
Okay, well, but so you work on this, right? Or sorry, do you work on bisimilarity on BPP nets?
I worked some time ago.
Okay, cool.
We can talk later.
Yep. All right.
Okay, I don't really see any more questions. So,
well,
what?
Actually, I have one more question. So, how this coffee break is organized on the?
Yes,
Zoom?
I was planning to comment on it now. So first, let's just well, thank Chana, but I guess everyone on their own.